Start the recording. Class is officially started. Um, uh, Happy Monday. We are into week 5, so we are officially more than halfway done with the course. Uh, Hopefully that is good news, but maybe not too good news. Um, as a reminder, the midterm exam is 2 days from now, so July 10th, Wednesday. Um, Good news being that class is more than halfway over. Um, uh, Terrifying, right? Anyway, the midterm is during class time, July 10th. Um, if you are here, if you've already emailed me to schedule it for a different time, I have that down. Um, if you need to take it at a different time, I would highly recommend emailing me as soon as humanly possible because it is 2 days from now. Um, but I guess like logistics of that, you'll show up to the same like Zoom link as normal class, and I guess this goes for people taking it at the regular time as well. Um, I'll be there to proctor. There might be some other TAs there to help me proctor, I guess. You'll need to keep your camera on, and you'll need to have like something to write with and like something to write on. Um, the exam itself will be administered through Gradescope, so we'll have like a PDF uploaded to Gradescope that you can take a look at, and you can like write down your answers and then take a picture or scan it up into scan it and upload it or something like that. Um, if you're not taking it at the normal class time, please do not open the Gradescope exam because it'll have like a 1 hour timer, and so once you open it, you won't be able to access it after that, and you won't get credit for it unless I've seen you come to class at the appropriate time to take it. We'll be able to do the exam on a tablet. So my thing with that is like, honestly, yeah, that's fine. You can do it on a tablet and upload it that way as well. Um, to some extent, this is going to be like, don't cheat. Um, but hopefully you know not to cheat and you've signed like the Purdue Code of Conduct and whatever. Uh, but yes, yeah, you can do the exam on a tablet. Just something to write with, something to write on, and some way to upload your written solutions up to Gradescope. Um, that's yeah, and yeah, so you won't get credit unless I've seen you come to class, like come to the Zoom link and like sort of take the exam proctored in front of me. Um, so yeah, don't try to like open it at a different time and take it by yourself and submit something like that won't work. Um, any questions about the logistics of the exam? You can write in a notebook, like it just the um the point I want to make is like it won't be something that you can like type your answers in on the computer. So you should have some way of like writing down your answers and then uploading your answers to Gradescope. So uh yeah, you can write it in a notebook, loose leaf paper. You can do it on a tablet. Um, you won't be able to like download the PDF to like write directly on the PDF. So if you're relying on being able to do that, you won't be. Um, but other than that, you should be able to just kind of uh, just show me your answers in some way, right? Um, are there any questions about exam logistics? So again, 2 days from now at this time, so like 48 hours from now, if you have emailed me or if you've talked to me about taking it at a different time, that's fine. Show up to the same Zoom link at the time that you're scheduled to take it. I would suggest showing up a few minutes before the time you're scheduled to take it. Um, and uh, keep all the same stuff applies, right? You'll need to have your camera on, you'll need to have something to write with and something to write on, and you'll take it in the same way. All right. Any other questions before we move on from exam things. Oh, we'll do an exam review session tomorrow. Hopefully I can get through all the content I need to today. None of the content from today is going to be covered on the exam. So the cutoff was on Friday, right? So it'll be through binary search trees. We won't talk about KD trees or anything. I released a couple of practice exams. Unfortunately, I don't have solutions that I can give you for the practice exams, but as I mentioned on Piazza, I do encourage you to sort of post your own solutions and like talk about it. I don't know if y'all have like a group chat or shared Google Doc or something like that. If you do, I don't need to know about it, but like feel free to study in whatever way you find valuable. Um, it's not open book, no. Um, yeah. Um, but yeah, so take a look at the practice exams. I would encourage you to take a look at the homework assignments. Um, practice the problems there. I've released solutions for problem sets 1 and 2. I won't be able to release problem set 3 because the the late due date for that I think is after the exam or maybe the day of the exam or something like that. So I can't release the solutions until until the late day is passed. Um, but come to class tomorrow and we can we'll go over things and y'all can sort of come with questions that you have or whatever and we can like clarify them. And of course I'll have office hours tomorrow to talk about that as well. So, and you can always post on Piazza and sort of figure things out that way. I think that's all I want to say about exam stuff, unless there's any other questions. There's also a problem set, I believe, which is due this Friday, July 12th, problem set 4. Problem set 3 was due yesterday. You will have until Friday to submit it if you use up to 5 of your late days. So yeah, late day for problem set 3 is on Friday, and then the the due date for problem set 4 is on Friday. The late day for that is next Wednesday. Make sure you've taken a look at those. Work on those if you haven't already. Um, there's also a programming assignment out. I see that there's a handful of solutions in here already, which is pretty cool. We will be talking about stuff related to the PA today in class, so hopefully that should be helpful. But yeah, just there are assignments floating out in ether. Make sure you take a look at those. We are currently working on grading problem set 2. Hopefully the grades for that should be released in the next couple of days. But either way, the solutions have been posted, so you can sort of take a look and like have a good estimate of what you expect your grade to be on that. All right. Yeah. Any course logistics questions before we move on to content? We have one remaining problem set after this week. Which 2 weeks won't have problem sets? We have 2 remaining problem sets because there's going to be 6 total. So the last week won't have a problem set because it's the sort of like finals week or whatever. So yeah. Yep. Any recommended app for scanning exams? I know like Cam Scanner is a thing which I've used to some success in the past. Um, if you are able to just like take a picture, like just a photograph of your paper with the answers on it, as long as yeah, like taking pictures is fine. As long as it is legible. Like if you write with like a dark pen or something like that, like as long as I can read what you've written, that's fine. Yeah, you all would probably know better about like apps to scan with. Uh, who takes exams in pen? That's a really good point. I don't know. Uh, Yes, there'll be three programming assignments. So there'll be one after PA2 is done, and I expect that to be that'll have some sort of flavor of like solving a maze or like searching through a maze to like do something, and that'll be more relevant when we talk about graph algorithms after the exam. All right. If there's no other questions, we can get started. Okay. Can everyone see the whiteboard? The exam is 1 hour. How many questions are on it? You can expect there to be probably like 5 or 6 questions, depending on if certain things end up getting split or merged together. Um, but yeah, 1 hour. The I guess I posted this on Piazza as well, but the topics you can expect us to cover are linked lists, stacks, and queues, searching algorithms. So in particular, insertion sort, merge sort, quicksort, and heap sort. Um, uh, big O notation, asymptotic complexity, dynamic programming stuff, and then trees like binary trees, binary search trees, that sort of thing. And so you can expect there to be something morally similar to like one question per topic. All right. Okay. Scribble, scribble, yes. Great. Okay. So if a dot just appeared on the whiteboard, oh, that's fine. Okay, here we go. All right. So on Friday, sort of like the last few minutes of class on Friday, I kind of like tried to rush through this idea of KD trees. I figured I could maybe try to do the topic a little bit more justice today. And in particular, we're going to talk about other spatial indexing algorithms and spatial indexing data structures besides just KD trees. So write this, spatial indexing. The idea here is we want to store a set of spatial objects, right? I'll explain what I mean by spatial. And we want to maintain closeness, right? So two objects that are close to each other should be easily accessible from each other, right? And by spatial, I mean this has like a position, maybe a size. And in particular, this will be like something in Euclidean space, right? So like R2 or R3, right? That's the idea, right? So a set of spatial objects. So this could be like a point cloud, right? Like a scattering of points, or it could be a bunch of like literal objects in a scene, or it could be like mobs in a game or something like that, right? Like hitboxes, right? It could be sort of anything that you can anything where you might uh, imagine caring about whether two things are close to each other. Um, you might consider using spatial indexing or a spatial indexing data structure, right? So the idea here is like, right, we want to maintain some kind of closeness. So we want to, this is useful if, for example, I want to know whether two things are colliding or if there's any like pair of objects in my scene that are intersecting each other, right? So naively, if I have, and all of my examples here are going to be 2 dimensions, just because I can't draw in 3D. But hopefully you can think about extending anything that we talk about to 3 dimensions or like arbitrarily many dimensions. Um, but yeah, so if we have like a scene, we've got a bunch of stuff, right? And maybe like these two intersect right here, right? Um, the the naive way of figuring out whether two things whether there's any pair of objects that intersect, right? Or like if find any pair of objects that intersect, right? Maybe we're writing like a physics simulation or something, and we want to make sure if two things are intersecting, we like push them apart or like we sort of like bounce them off each other or something like that, right? Um, the easy like the naive thing we can do is for I equals 0 to n, where n is the number of objects, right? And then I can say for j equals 0 to n, if I equals j, skip if object I intersects object j, return j, right? And so here I loop over every single circle and every single circle. Like I loop over every possible pair of circles. If I'm looking at the same circle twice, obviously I don't care about that as an intersection, so I skip it. If I've got two different circles that intersect each other, I return that as an intersected pair, right? And maybe I like do whatever I actually want to do with an intersection here. Anyone want to shout out what the complexity of this is? Shout it out or drop it in chat or whatever. O of n squared, exactly. Yeah. Also theta of n squared. Yeah, it's quadratic, right? Because I loop over every possible object, and then for each of these, I loop over every possible object, and then I do some like roughly constant time test, assuming I can check to see if two things intersect in constant time, which makes sense. So yeah, this is O of n squared, and again, O of n squared is maybe not terrible, right? It's still polynomial time. If n is like relatively small, then that's fine. But you'll notice that like a lot of these iterations are spent doing very silly things like testing to see if this and this circle intersect. And like clearly they don't, right? We can look at this and say like obviously these aren't anywhere near each other. Or like do this and this intersect. Obviously they don't. And so the idea is we might want to use some better way of storing all of these so that we don't have to test every object against every other object. Right? So the first sort of approach I'm going to talk about is something I'm going to call like spatial hashing. And we'll talk more about hashing probably like Thursday and Friday after the exam. But you don't need to know a ton about hashing to sort of understand what spatial hashing is, right? So the idea is I take my 2-dimensional space here and I break it up into a grid, right? Maybe I make it a 3x3 grid, right? And every like every grid cell just holds its own set of objects contained inside it, right? So this grid cell only holds this one only holds one, this one is empty, this one only holds the one, this one holds, I guess, two, right? Maybe we merge these cells together. This one holds two, This one holds the 1, the 1, and the 1. And now, if I want to see if two things collide, I can look at each grid cell individually, right? Because if there's a collision, then it's going to be with something in that cell, right? Assuming my cells are big enough and assuming things fit entirely into a cell, um, which you do have to worry about, in fairness. But now I don't need to, like, if I want to see if anything collides with object I, right? All I have to do is look up, if I want to see if anything collides with like this particular circle, all I have to do is look up what cell it's contained in, and then just loop over the other objects in that cell, right? So I never waste time checking for collisions between like this and this or this and like something that's super far out because they're not in the same cell. So I don't ever have to worry about it, right? The idea is you just take your very big space with a lot of objects and you break it down into a bunch of smaller spaces with their own sets of objects. And if you ever care about a collision or if you ever want to like see what's close by, all you have to do is like compare it to the spaces around it, right? How do you determine the size of each cell? Vibes. I don't know. I mean, the like it depends, right? If you make the cells too small, then you're gonna have objects that span across multiple cells, and that's going to be a problem. If you make the cells too big, then you're like searching a lot of objects. So you sort of like you hope that you know something about your scene or like something about the domain that you're doing this in, and then you use that to like determine a good cell size. Or you pick something and you try and you say, okay, this is clearly not big enough, so let me make it bigger, or let me make it smaller or whatever, right? Um, so that's the idea. Uh, yeah. So maybe we can define like a data structure for this, right? So um, each of our objects, well, actually, how do I want to do this? Yeah, okay. So let's say we've got like an array of objects. Oh, wait, this is C, right? Okay, I'm gonna call this array O. Um, we have, let's say, an array of cells. We have a function from object to the set of cells that it exists in, right? So maybe right. And this can do something simple like computing its coordinates and just like rounding them to the nearest box, right? And then each cell has a list of pointers to objects, right? Maybe we can say maybe like int, right? And then our scene is just an array of cells like this. To add something to the scene, we take the object, we hash it, and for each cell in the hash, we add um, we add our object to that cell's array of objects, uh, and then we're good to go. If we want to test to see if two things intersect, or if we want to like find everything that intersects with a particular object, we look up all the cells it exists in. We look at all the other objects in those cells and just test those. And so we never waste time testing objects that are not in the same cell, right? Um, so this is good if you've got a nice like hashing function, right? If you've got a nice way of like putting things into a cell, which of course you can just do by like rounding, maybe my cells are like 10 by 10, right? So I just round the coordinates of my point to the nearest 10. right? Round the x and y coordinates to the nearest 10, and that gives me that tells me what cell it exists in. If so, it's nice for something like that. Um, the there's obviously a lot of like memory overhead, right? Because we've got a bunch of cells that all might hold references to the same object because these objects might have like sizes that overlap, that like go outside the bounds of a particular cell. Um, and so there's more memory overhead for that. There's also like all of this indirection. Like we have to hash the object to get what cells it exists in, and we have to look up those cells to look at all the other objects. And there's a whole bunch of indirection. But if your scene is like uh, maybe uniformly distributed or like very nicely spread out, then you can maybe pick a cell size that gives you a reasonable number of objects per cell, and then you don't have to do as much work. Um, so pros and cons. Um, that's all I really want to say about spatial hashing. Um, any questions on that before we move on? Okay, we're gonna go into are we gonna go into the hashing function? We'll talk about hashing functions in a more like generic sense, like I said, probably towards the end of this week. The particular hashing function for like coming up with the set of cells that an object exists in, um, you can kind of determine based on what your objects look like and what your cells look like. But like I said, like one very easy thing to do is just round, right? So maybe I want my hashing function to give me the index of a cell, and maybe I've got like points, right? So I can take my x, y, and I can say like um, int x divided by 10 times 10, comma, y divided by 10 times 10, right? Maybe this is my hashing function, right? So it takes some like xy coordinates and it outputs the coordinates of the 10 by 10 cell that that point would live in, right? So if it's like 25 comma 35, then this would live in cell 2 comma 3, right? So it sort of depends. Yeah. And like to be clear, your cells don't actually have to be like grid cells, right? They can be whatever like weird way you want to partition your space, as long as your hashing function knows about it, and as long as your hashing function can like put things in the appropriate cell. So really a lot of the like the power of this, or like the magic here sort of comes from having a good hash function. Um, anyway, so that's spatial hashing. Uh, you'll see this used a lot in like um, I don't know, like astronomy type things where you've got like stars all over the place, and you want to like compute hash values to figure out like what stars are close to each other in the night sky or something like that. I'm not an astronomer, so I don't know much about this. Is there any way to know whether a cell division is better or worse, like grids versus squiggles? Uh, no, I mean try it and see if it gives you what you want, right? If your objects are very uniformly spaced across a grid, then probably grid cells are going to be better. If your objects are kind of like arranged in diagonals like this, then like trying to fit a grid to it is probably going to be kind of weird, but like splitting these up into diagonals is going to be a lot nicer, right? So you kind of um, this sort of relies on you knowing something about your data set. And we'll see is like often going to be the case, right? With spatial indexing stuff, is like if you know something about what you expect your data to look like or what you expect your scene to look like, then you can do a lot better. Um, so yeah, good question. Okay, the next thing I'm going to talk about is I guess I'll sort of talk about like KD trees. Maybe I want to separate this out. KD trees and quad trees. Um, so as I sort of like whirlwinded through on Friday, the idea of KD trees is basically like, what if we took the idea of a binary tree and sort of extended this to multiple dimensions, right? So again, we're starting with a bunch of points in I'm drawing 2D space, but this could be, you know, whatever you want. The D here is the dimensionality, right? So this could be like 3D or 5D or whatever. So we start off with a bunch of points, and like I said, like with a binary tree, right, or like a binary search tree, if I've got points here, and I want to find two points that are close to each other, or I want to like see if a particular point exists or something like that. Um, a binary tree lets me do this more efficiently than just a linear like theta then scan, right? Because I can take my one-dimensional like line of points and I can split it somewhere. And then I get two smaller lines and I can take each smaller line and split it somewhere. I can take each smaller line and split it somewhere. I can just keep like recursively splitting these things until I end up with like a um, maybe the way I want to draw this is like here's here's the entire line. I can split this into like, oop, I am so bad at here. There we go. I can split this into like two pieces like that. I can split each piece into two pieces like that. And so now, if I want to find this point, I look, okay, it's in this entire bracket. So I'll keep looking. I don't have to look at this left bracket at all. So I can cross that out. I don't have to look at this right bracket at all, so I can cross that out. And so now I've very quickly narrowed in on the place where that point might be, right? And so now I can look to see if there's anything by it. And then I get my answer, right? So KD trees work sort of the same way, except now we've got a bunch of dimensions to reckon with. So I take my plane and I pick either like horizontally or vertically, right? I pick the index of a dimension to split it along, and then I pick a place to split it. And again, right, this is a lot of choices. We'll talk about how you can make some of these choices, but for now, let's say I split it like this, right? And then now I've got two subplanes, right? I can sort of recurse. So I can look at maybe the left subplane and I can split it like this. And I can look at the right one. Maybe I want to split it right here. And then I can sort of keep recursively subdividing, right? So I can divide that, and divide, maybe I want to divide this here. And there's no reason to assume that the way I'm dividing things is like particularly good right now. I'm just drawing a picture. But yeah, so we've recursively subdivided all of this down, right? Now, let's say I want to find this particular point, or I want to see if there's a point here, right? I don't have to scan through my entire set of points. I can look at this, I can look at the space, I can look at the first division and say, okay, it's this vertical line. The thing I care about is on the left side of the line. So let me just cross out everything on the right, right? And now I look at this space and I see that I've divided it with a horizontal line. I say, okay, the thing I care about is at the top. So I can cross out everything on the bottom. And so now I've gotten rid of like 3/4 of my space already, right? And now I look at just this and I say, okay, it's divided along here. So it'll be on the left. I look at this, okay, it's divided along here. It'll be on the top. So now I've narrowed in to just this region here. Now I can say, okay, this is not divided, so let me just loop over all of the points in here. And I look at 2 points instead of all of the points, right? That's the idea of a KD tree. How do you divide this? Well, one sort of naive thing that you can do is always split down the middle, right? So if my space goes from like 0 to let's say 16, the first split I'll just do at 8. And then maybe this goes 0 to 16. This split I'll do at 8. And this one I'll do at 4. This one I'll do at 4, right? This one would be at what is that, 12 or something, right? I can just split it in half every time. This is fine if I'm given some nice bounds on my space ahead of time. Like I know it goes 0 to 16 and 0 to 16. Um, this is also good if I know that my points are sort of uniformly distributed. That might not be the case. Actually, maybe I want to talk about why we want these to be uniformly distributed. Sorry, I'm kind of all over the place here, but uh, let's talk about the time complexity of finding a particular point in a KD tree, right? So obviously, the naive approach is I just say for I equals 0 to n if object I dot x equals x and object I dot y equals y, return I, right? So this we know is theta of n, right? Um, can you help me write pseudocode for searching for an XY pair inside a KD tree? So let's say we start with we have some XY that we want to find, right? Maybe I'll say something like find XY, then tree, right? I guess what does a tree struct look like? Um, we need to have a list of points, right? Um, maybe a proper array of points. And then if I'm splitting, I need to know where I'm splitting. So uh, maybe I can say like I can say maybe int split location, right? This will be either X or Y. This will be like the coordinate. And then I've got T1 and T2, right? Does this make sense? So I have an array of points inside my tree, right? This will be non-empty if this is a leaf node in the tree. Um, if it's not a leaf node, then I'll have it'll be split along some particular dimension. So this will tell me that it's split along like maybe x equals 3 or like y equals 5 or something like that, right? And then if it's split, then I have my left and right subtrees or top and bottom subtrees, right? So given this data structure, how might I write a find? Well, the easiest thing to do is if uh, num points, maybe actually, let's just say like if this is a leaf, right? Uh, a tree is a recursive data structure, so maybe I want to write this recursively. So the base case of my recursion is if it's a leaf node, then I just do a for loop, right? This for loop is just this thing right here, right? There's nothing better I can do if I've already like broken it down into a very small set of points. Otherwise, if this is not a leaf node, what is my uh what sort of recursive calls do I spawn? Someone want to shout it out? Yeah. So the base case is this, right? So what is the recursive case? I want to see if X is greater than split, well, yeah, we need to know what axis, right? So if um, axis is probably a better word. Okay. If axis equals X and X is greater than split, this is, tree arrow axis. This is tree arrow split. Then we recurse on find X, Y, and then tree arrow T2. Else if axis equals X and X is less than or equal to split, then we recurse on tree T1. Else if axis equals Y, dot, 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 right? If it's Y and Y is less than the split, or Y is greater than the split, we go to T2. If it's Y and Y is less than or equal to the split, then we go to T1, right? And we just kind of keep recursing down until we hit a base case here. And if it's a leaf, then we just loop through all of the points in that leaf node. Does that pseudocode make sense? Do people believe me on that? So here we'd match the X and then move up or down for Y. Yeah, so here we would, in this example, we would say, yep, we're splitting along X. So we recurse on T1 because X is less than the split value. And then we say we're splitting on Y, so we'd recurse on T1 because Y is less than the split value. And then, I mean, I guess in this case, we're always going to T1. But yeah, that's the idea, right? So our tree starts as this, and then T1 is this piece to the left, and T2 is this piece to the right. So we recurse on T1, and then we recurse on T1 again, we recurse on T1 again, we recurse on T1 again, and now we've got a leaf, so we just check these two. We really just use these to reduce the amount of points to check, but we still want to do things like the distance formula. Yes, exactly. So if what you care about is like how close 2 points are, then yes, you're still going to have to use the distance formula at some point. It's just now you don't have to compare the distance of every point to every other point, right? So this really just like reduces the amount of work that you have to do in that sense. Yeah. So it's like a sanity check. I mean, it's really if you've built this correctly, this is in fact making your algorithm a lot more efficient, right? Because in sort of one step, we're eliminating 1, 2, 3, 4, 5, 6, 7, 8, 9 points, right? Instead of checking the distance to all 9 of these points, we're just comparing one coordinate, and we're saying, oh, its x value is less than this, so we don't have to look at any of these points. Right. So just like a binary search tree where like you instead of scanning through the entire list, you just like in one step you sort of eliminate half the list, right? That's the idea. T1 and T2 are subtrees. That's right. Yeah. Right. So normally we think of a tree, or we think of our like recursive definition of a tree as like um, struct tree. You've got like some value, and then you've got like 3 pointers to the left and the right. How much time would this take to build? Filling up the tree would be part of the hashing function. So here we don't need a hashing function, right? Um, we're not here, or I guess maybe the way to say this is like here the hashing function is fixed in the sense that we're hashing based on whether the point is to the left or the right of the thing we care about, or above or below the thing that we care about. How much time would this take to build? That's a very good question. We should figure out what the time complexity of, actually, we should figure out what insertion looks like and then look at the time complexity of that. Um, on that note, what is the time complexity of find before we write pseudocode for insertion? Right, so here, if it's a leaf node, um, I just loop through the things in that leaf node. Ideally log n, right? Um, the reason we can say that is because if I've built my tree well, then at every step, um, the the number of points in the subtree that I'm looking at is roughly like right, or it's like reduced by some fraction. Of course, if if my if I'm not smart about this, right, and if my points are all up here, right, and I say, okay, I'm going to start splitting. So I'm going to split here. I'm going to split here. I'm going to split here, right? These three splits have done absolutely nothing for me, right? So I should have like, if this is what my KD tree looks like, then it's still going to be like theta of n, because this is the equivalent of having like a binary tree that's just a linked list, right? Um, so you do want to sort of keep this balanced. And then the other thing is we do still have a loop here, right? But if we are if our policy for splitting the tree is like keeps this as a constant, then this loop doesn't matter, right? So maybe we can talk about good ways to build these trees to make sure that we keep that log of n complexity. So first of all, we want this to be balanced. So um, you might like you pick either axis like x or y, and then you find like the median among the x points or among the y points, right? So uh, maybe you say like split equals median of point dot x for p in points, right? And the idea here is point dot x or point dot y, depending on the axis that we picked here. The idea here now is we take the like, if it's a median, then we're guaranteed that half the points are going to be below it and roughly half the points are going to be above it. And so we know that every time we split, we're dividing the number of points in two, right? That is good, except for now building this tree picks up this O of n factor because we have to loop over all of the points, right? Which is not great. But sort of similar to like in quicksort, right? You want to find a partition that's like roughly halfway through. And so of course you can always build a tree that's very bad for this, where like you can like build a set of points where every time you try to pick a pivot, it partitions things into 0 and n-1. But anything that works for quicksort for picking a good pivot is going to work here, right? So maybe we can like sample 5 points and take the median of those 5 points. That's still constant time because we're always sampling the same number of points, but we know for a fact that we're going to get at least 2 on one side and at least 2 on the other side. And if we're sampling randomly and the data set isn't like specifically constructed to be like a worst case scenario, then we'll do pretty well, right? So constant time approximation of median, right? The other thing is, when do we know to stop splitting? So one thing you can do is just split out to a certain depth. So just like we say, we're going to split 3 times. We don't need to sort and get median, but just for robustness. Yeah, so you could, right? I guess the median is actually like n log n if you sort and then look at like halfway through. There are big O of n algorithms for the median that just have like a very, very big constant in front of the n. But you could, right? You absolutely could do that if you don't care about the cost of building the tree, right? Um, So if this is something like you've got a fixed scene, you're building the tree offline, and then you just really want like queries on this tree to happen really fast, then it doesn't matter if I spend 2 days. If my program spends 2 days running building this tree, because I can just like pay the cost of those 2 days up front, and then my game is really, really fast. Right? So in that case, maybe this is something that you care about. I mean, n log n is still going to be pretty terrible. So yeah, you want some kind of like approximation of the median, maybe. The other thing to look at is right, we can split down to a certain depth, at which point we're going to have roughly n over 2 to the d points per like cell per leaf node. Maybe that's fine. Maybe that's all we care about. Or maybe we've got maybe you want to keep splitting. And so we can say split to a fixed depth. Or the other thing is maybe we want the number of the number of points in a leaf node to be constant. So split until node has less than or equal to k points, right? Where k is some constant that we pick. Maybe k equals 8. Maybe it's 1. So you sort of keep splitting until each leaf node has exactly 1 point. But you don't have to, right? You can kind of choose how far down you want to split this. And of course, the more fine grained you want this KD tree to be, the longer it's going to take to build. But more likely, the faster it's going to query over things, because you're going to be able to like prune out a lot of things at once. And then how do you decide what axis to split along? So one thing you can do is just alternate, right? You don't always want to pick the same axis, because then you get something like then you just end up doing something like this, right? You just get like finer and finer stripes like this. And then we're not distinguishing points based on y coordinates at all at this point, right? That's bad. Like we could obviously do a lot better. Or I guess like the thing to think about here is like the median of these points is going to be very, very close to all of them. And so figuring out what this median looks like, there's going to be a lot of margin for error. Like if we're off by 1, then all of a sudden it's going to put everything on one side, right? So if you think your points are uniformly distributed or like roughly uniformly distributed, then if you alternate between X and Y every time, that's fine. Otherwise, you can do something like look at the set of points that you have and figure out if they vary more along X or Y, right? So you look at the minimum X and the maximum X, and you look at this range, and you look at the minimum Y and the maximum Y, and you look at this range. And then whichever range is bigger tells you which direction to split along, right? And this tells you something about like you're not going to be like you're not going to get these like very tall and narrow strips, because tall and narrow is sort of bad, right? That's something else that you might care about. In more information theoretically, like the thing you maybe care about is the entropy along X or the entropy along Y, right? If these are words that mean something to you, but this is sort of how like decision tree training works, right? Like gradient or not gradient. What is this? Yeah, like training. So it's like how scattered are the points along X and how scattered are the points along Y. So if all of the points fall very neatly into the same Y coordinate, but they're scattered across X, then X is the thing you want to split along, because knowing something about X tells you a lot more about the point than knowing something about Y. That's the idea. I'm not going to talk too much about entropy. This is not like a discrete math class or whatever, so we're not going to get into that. But the idea is like it's the same thing as like the spread, right? The range. So different ways that you can figure out like what dimension or what axis you want to split along, where you actually want to split, when you want to stop splitting. inserting into a KD tree in the last few minutes, maybe we can write some pseudocode for that. Right. So obviously the way to build up a KD tree is you start with an empty KD tree, you take your list of points, and then you insert each point one at a time. So insert X, Y, tree. The first thing I want to do is say like tree dot points dot append X, Y, right? If sorry, not necessarily. Again, this is a recursive algorithm. So let's induct on what tree might look like. If it's a base case, right? Then I want to say 3 points append XY, right? Otherwise, if it splits like tree.axis equals X and X is less than tree.split, then we insert XY tree.T1 and so on, right? If the axis is X and we are greater than or equal to the split, or maybe I think I said less than or equal to here, right? So if we're less than or equal to the split, then we insert on T1. If the axis is X and we're greater than the split, we insert T2. If the axis is Y and we're less than the split, we insert T1. If the axis is Y and Y is greater than the split, we insert T2, right? Does everyone buy that this is the correct pseudocode, or has anyone spotted a mistake? If anyone spotted the mistake, you want to tell me what the mistake is? And there's a very crucial thing that we're missing here, right? Yeah, so I'm the dot 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 is sort of eliding over the fact that I don't want to write morally the same thing 4 times. What happens if I start with an empty tree and I insert a whole bunch of points into it according to this algorithm? Segfault. Okay. What happens if I start with a single leaf node tree? The tree needs to be split. Yeah. So here, um, after points, uh, after tree dot points that append x, y, we now also need to check to see if need to split, then split, right? And then our split function can do all of the stuff that we thought about like over here, right? All the way over here. Yeah. So our split function now can decide x or y, which or like where to split, right? Need to split can think about enough points, enough depth, right? So all of the like decisions that you make when you design a KD tree sort of go into this need to split and your actual split function, right? But yeah, once you've picked an x coordinate, once you've picked an axis to split along and a place to split, you just spawn 2 new trees. You insert all of your points into the 2 new trees based on like you decide which tree to insert them into, and then you do that and you sort of recurse, right? That's insert. Um, if your tree is balanced, then the depth of the recursion is going to look something like log n. The only like if this has something that looks like O of n, then this is going to become something like n log n to actually insert all of the things, or to actually insert a single point, because you're going to have some kind of like O of n scan, which is why you want your like figuring out where to split, you want that to be roughly constant time. Um, and so then you just get log of n. And so to build the entire tree out of n points is going to look something like O of n log n, or theta of n log n, right? So theta of n log n to build the tree, and then theta of log n to traverse. Okay. And then, wow, I really do just like say something at the very end of class. The a quad tree is like a KD tree, except we always split it into four pieces, right? So we always get four subtrees with the northwest, northeast, southwest, and southeast. And we always, split along the middle, right? So yeah, a lot fewer decisions to think about when you're building a quad tree. Usually a quad tree will just go out to a fixed depth. Um, no attendance. Sorry, I forgot to make an attendance poll before 9:43 a.m. So quad trees are great. Yeah. A lot of like game engines will use quad trees when you insert a bunch of uh stuff, like a bunch of objects into the scene. Um, they'll store them in a quad tree so you can like very quickly do spatial indexing. Like, you cast out array like to see what to draw on the screen. You're just like look at the quad tree portion that's actually being rendered. Um, and so you can kind of do it that way. If this is in 3 dimensions, you'll call it an oct tree, right? Because now you've got like a cube or something like this. I don't know. Pretend I can draw. I can't draw, but you get the point, right? It's like a yeah. I'm gonna stop the recording here.